This is the 7th year that we've done the EBM course. It was started by the Department of Pediatrics. Raleigh McGrath, who's the chair of the Department of Emergency Medicine, took it over. Then, as the prerogative of all chairs, he dumped it on one of his faculty, Dr. Tony Sapal. You're going to have 4 lectures. This one, which is an overview of EBM and therapy. There's a bonus today. We're going to go through the calculations that you need to understand therapy, directly from the article you're going to be reading. Jamie Jones will talk about diagnosis. Carrie Chisholm will talk about harm. And then I will return to change your minds about statistics. And what that really means is how to use numbers in clinical practice and in your daily lives. I am going to change your mind about statistics. You need to know a little about me. Who am I? I'm Bill Cordell. I'm an adjunct clinical professor in emergency medicine. I practiced for 21 years. Now I'm at Eli Lilly as a full-time researcher, still maintaining my appointment, and I teach national workshops on evidence-based medicine, research design, computers in medicine. I love this stuff. But here are our goals. I'm going to give you today the overview, the big picture, the roadmap. I'm going to give you the structure of what's going on. The greatest teacher I had in medical school was a pathologist. You go, pathology. What he did, he was gifted. He came in and in 2 weeks gave us an overview of the entire semester, then tested us on that structure. Then we went back and hung the meat on the skeleton. It was the most fabulous class, and it really inspired me how to do this. Another very important thing is we're going to learn to speak the vocabulary of medicine. Every year or so, you'll read in a newspaper, somebody puts on a white coat, goes in, knows how to talk doctor, and nobody suspects that they're really a complete imposter. Kind of like the movie Catch Me If You Can, where he just knew how to speak like a pilot and nobody questioned him. Vocabulary is very important. Don't panic. What I usually show is the symbol that nobody used to recognize. It's from the Hitchhiker's Guide to the Galaxy. Now everybody knows it because they remade the movie this year. Don't panic. No one masters these concepts overnight. It does require hands-on practice. That's why they're the small group sessions. And when you get to diagnosis, don't freak out. It's a little bit harder than therapy. So just cut yourself some slack on that. You really have to sit down with a pen and pencil and work that out. I'm going to ask you a very pointed question. You all have busted your behinds to get here. You've been selected from a group of highly competitive peers. Now you're here. What's the job description of a doctor? What you're going to be doing? Uh-oh, I see deer in the headlights stares. It's one of those questions, it's an existential question that drops most people in their tracks. What do doctors do? Well, let's go through that. What a doctor does is first, the humanistic aspects. By the way, you don't need to take notes on any of this. Relax, have fun with me. Raucous applause. Everything I say will be on the website, everything, except the jokes, and that's what I want you to remember. Fun, number 1. Doctors provide humanistic or doctoring qualities. That includes comfort, relief of suffering, teaching and advising, communication, listening, compassion, care, the art of medicine. There's also a business side that has to be mastered. We have to be stewards, good stewards of resources. There are technical issues, surgery, putting in IVs, those kind of things. All these encompass why you're here, to learn all these. But there's one really important aspect. What does MD stand for? It stands for make decisions. One of the main purposes of this evidence-based medicine course It almost could be titled clinical decision making. Very important. How many are DOs? Because we'd have to also say decisions, I guess, overall. What kind of decisions do we make? Treatment. Should I add an inhaled steroid to oral steroids for asthmatics? Diagnosis. Should I order an abdominal CT scan in my patient with suspected appendicitis? We're asked to make decisions, but we're also asked to predict the future. Where do we predict the future? Think of something. What's the classic line? Doc, tell me what my chances are. Then you gaze into your crystal ball. People ask us to do that. Or, if I use a cell phone, am I going to get a brain tumor? Do you wonder that? Now, my question for guys is, since the phone is here and the guy brain is down there, does it affect the guy brain? You can ponder that in your quiet moments. Raucous applause. All right, you're on cue. Thank you. Doctors are also scientists. Our profession is called medical science. You are in the medical science building. So what is science? We're going to talk about three things: what it is, what is bias, and what are confidence intervals. You're also going to learn, by the way, how to look at research design. Very important. But in this introductory, I want you to know what science is. Science is a way of knowledge that is systematic. Whenever you see the word systematic, it means there's a system. It is reproducible. Another scientist could come in and reproduce the work and refute or confirm. Finally, science must also be measurable. Everything we are going to look at is measured with numbers. It's not these very loose concepts. Science has to have a number behind it. That's why our final session together is going to be about numbers. Very important. Science seeks to minimize bias. Here's a nice quote. Smart people, like smart lawyers, can come up with very good explanations for mistaken points of view. Let me read you a quote from Marion Barry, then mayor of Washington, D.C. Outside the killings, Washington, D.C. has one of the lowest crime rates in the country. That's how people play and fool with numbers. One of the things we're going to teach is how to be a critical thinker, how to learn to look at numbers or statements and say, with a very critical eye, does this make sense to me? Is the evidence there to support that statement? What is bias? I suspect most people, when they hear the word bias, think of prejudice. Well, in a sense, that's correct, but in science, bias has a little different meaning. Prejudice means we've prejudged, or we've come to conclusions before that. Bias, in science terms, is a little different. We are in a research project taking a sample. For example, we want to study people with headache and see if a new treatment works. Can we go through the world and test every person with headache with our new drug or our control? Of course not. We can't do that. It's impractical. You can sit and think of all the reasons that would never work. So what do scientists do? We go in and we grab a sample that we try as much as possible to make representative of the whole world of people with headache. Sample, then we take and study that sample. We draw conclusions, and then we generalize back. We make a statement about everybody with headache. Sample going to the truth in the universe. What can go wrong? What can lead us astray from taking the results from that sample and moving it to the whole universe. What two things can deviate us away from the truth? One is rotten luck, chance. No matter how perfect a study is, there may be a chance occurrence that throws that sample results from the truth. The other one is bias. Bias is something we do in designing, executing, interpreting, publishing, or then bringing it to journals and reading them. Something in there goes wrong. There are at least 50 varieties of bias. Can you think of one? Have you ever heard of sampling error? You know, you watch these presidential elections and they're taking samples, polls. Do they always get it right? You might say, well, they sampled the wrong people. If you sample a group that already has well-formed opinions in one direction or another, you can see it's going to throw the whole results off. Bias is something inherent in how we do the study. Chance can also throw us off. Scientists also think in terms of confidence intervals. The other word that you'll hear is error bars. Science, at its very foundation, is humble. Scientists don't believe we have the answer. The answer we gain in science is always surrounded by an error bar. Means we're pretty sure that that answer that we got falls somewhere in that range. And you will hear this translated in virtually every article you read into a confidence interval. And most commonly used confidence interval is the 95% confidence interval. When you read a newspaper and it says 51% of people drinking milk develop brain tumors. What is that 51%? That's one of the first questions we should be asking. It's what we call the mean, usually the mean, or the point estimate. What do we as scientists say? 51% plus or minus what? I want to see the 95% confidence intervals. That 95% confidence interval could range from, let me give you an example, 24% to 69%. That means as low as 24% could get cancer after drinking milk, and as many as 69%. What shrinks confidence intervals? What makes us more certain? Narrows our error bars. Sample size. The more people we study, we become more certain that our true estimate lies within those bounds. Error bars, very important. So we've talked about what it means to be a doctor. We've talked about the importance of decision making, science. What's all this got to do with evidence-based medicine? And here's the punchline. Evidence-based medicine is the translation of scientific evidence into clinical practice and decision making. It is learning to use research. You are not learning to do research. You are going to be smart consumers of the scientific research literature. Translation, science into decision-making and clinical practice. Now, there would have been a really fabulous slide at this point, so I'm going to mime it. There would have been one circle intersecting in a Venn diagram over here with a second, and over here with a third. It's like a Chinese ballet. I was just in Beijing. Those research circles, or the three circles of evidence-based medicine, are research evidence, combined with clinical experience, combining with values, rights, and preferences. Evidence-based medicine is the integration of all three of those circles. Three circles. One is research evidence, and in parentheses you can put rational. The second circle is clinical experience. In parentheses put emotional. The third circle intersecting is values, rights, and preferences. In parentheses put ethical. Nobody is here to tell you that decision-making is all about numbers and science. That's ridiculous. Let me give you an example. You are going to buy a new car. You're now in medical school. Your family knows that you're destined for greatness. They've given you a loan. Your old junker has died. You're going to go out and buy a car. What's the first place you're going to look? Are you going to get information? I bet virtually everybody is. What are you going to look at? Pardon me? I apologize. You'll look at consumer reports or an automotive review. What data are you going to get? You're going to look at gas mileage, safety, side impact, airbags. What else?
Five-year reliability rate.
Reliability. You're going to come out data rich. That's evidence. And it's probably done scientifically by these labs. Now you walk into that showroom, you know what you want. All of a sudden, you hear this heart music playing. There's this shine of light behind this beautiful red sports car with the world's worst mileage. No even back seat. Double your budget. I'll buy it. What has happened? Your emotional component has completely overridden the ethical. Completely. Do you think that happens in medicine? Wait till you're up 24 hours and somebody comes and asks you to make a decision for them. But I don't want you to think that experience is completely that kind of emotion. There are other emotions hardwired into us. Fear. The brain is fabulous at pattern recognition. People will make a diagnosis based on one look at things. You'll learn to pattern recognize EKGs, heart tracings, on and on and on. That's experience. It's emotional because it completely bypasses the evidential pathways. Then there's the value component, which we always consider in decision making. You know, is my decision ethical? Is this what is of value to the patient? By the way, how do you find out what patients values or prefer? Pardon me?
Talk to them.
Yes. Talk to them. Remember, we said doctors communicate. One of the fundamental principles that we're going to teach is it's not just doctors making decisions, but we have to involve the patient and family at their level, whatever that is, into the decision-making process. So we talked about those three circles. What are they? What is it? Research evidence, numbers. Clinical experience, emotional pattern recognition, experience. Values, preferences, and rights, ethical principles. Evidence-based medicine, why I believe it is such a nice teaching model, and it's not the only teaching model, is that it is very patient-centric. Everything begins and ends with the patient. It involves critical thinking, and it emphasizes small group learning, as you're going to see this, I believe, this afternoon. It really emphasizes how to teach yourself after you leave medical school and residency. Lifelong clinician education. And another very nice thing is how to rapidly access information. critically important in a world that is just glutted with information overload. It's also important to discuss what evidence-based medicine is not. Evidence-based medicine is not synonymous with critical appraisal of an article or going to journal club. People may tell you that, but it's not. Furthermore, it is not limited to academicians or statisticians. In fact, quite the opposite. It is aimed at frontline practicing physicians. Evidence-based medicine does not require statistical knowledge. It requires common clinical sense. We nevertheless do teach statistics, and I'm going to tell you, it's going to be on your boards. But there are other more fundamental reasons. People need more than ever to understand science and numbers. I will just give you an editorial comment that you pick up the newspapers and read how people are interpreting science today. I think we're backsliding. I think we really need to move back to an emphasis on science and numbers. Our country is desperately slipping. Just take a trip to China or India, and you'll understand exactly what I'm talking about. So I'm not saying numbers is the only way you live life, but we integrate it with those other very important components of ethics and experience. The key mistake and the key fundamental mistaken criticism of evidence-based medicine is that somehow it's trying to teach doctors to make decisions by evidence alone. How do you know that we've already refuted that? Why? How? Remember the Chinese ballet of the three intersecting circles. That tells you that this course is about three different things. And again, that's a model, but it's a very nice model. There are key concepts of evidence-based medicine that we want you to learn. One is that statistical significance does not equal clinical significance. We will talk a lot about that at the end. The second principle is the hierarchy of evidence. Not all evidence is created equal. What is at the top of the most credible evidence in science, medical science? If I ask you, tell me what's at the highest level that you're going to trust the most. It's going to be the randomized controlled trial or the meta-analysis. Analysis, for those who've never heard the term, is taking a group of randomized controlled trials and statistically combining the results. There are pluses and minuses to both approaches. What's at the bottom of the evidence rung?
Anecdotes.
Excellent, anecdotes. That's called the case report. That is a story. That doesn't mean it's not valuable. But many times case reports can be the exception to the rule. Like this patient grew a sixth finger after taking drug X. Well, that's 1 out of 17 million. It's an exception. But you can see the newspapers. Drug X causes growth of sixth finger. It happens all the time. What's good about case reports? I'm sorry? Exactly. Possibilities. Or it's like an early surveillance, an early warning system. That's how Kaposi's sarcoma, that's a cancerous tumor associated with HIV/AIDS. That's how it was first detected. So it can go either way. What's the lowest rung of evidence? You all know this. Politicians and used car salesmen. Now, in between those, at the top, meta-analysis, randomized controlled trials, also called RCTs. Then we have epidemiologic studies called cohort and case control. Don't write this down. You have a whole module on this. Then we have case series, which is a group of stories clustered together, and then we have case reports. Just because we don't have the best evidence doesn't mean we ignore it and give up. Many things, particularly those that deal with harm, don't have randomized controlled trials. So we have to use other methods to look at the situation. Why do we find so many poisoning and like the cell phones? Why don't we do randomized controlled trials on those? Pardon me? It is not ethical. It could cause harm. Sure. We're going to take this half of the room. We'll randomize this class. Half gets cell phone, half doesn't, and we're going to check all of you in 10 years for a brain tumor. Not only is that unethical, you're exposing people to potential harm. What's the other problem? We won't have cell phones in 10 years. We'll be talking using telepathy. And those, yes, they will have answering machines. The other thing is, we want the answer now. We don't want to wait 10 years. So there are other things that we have to do. That's exactly right. Now there's a very important thing called relative versus absolute. Differences, when we compare something, are always relative to something. Let me tell you a little story. In fact, I'll just ask you a question. What animal has the largest phallus in the animal kingdom? Humans? Not worthy of mention. Pardon me? Blue whale? Absolutely, the blue whale would probably win. But you didn't ask me the question. Relative to what? What animal in the animal kingdom, relative to its size, has the largest phallus? The flea. Now you know why they can pole vault so easily from dog to dog. Now, this gentleman wisely said another thing. If I said, what is the animal with the absolute largest phallus, then that puts us in a whole other category. Whenever you see relative versus absolute, I want you to think of the flea. Or conversely, when you see a flea on you, I want you to think about absolute and relative differences. All right, there are 4 important skills that you need to know. I don't want you to write this because I want you to memorize it. These are the 4 skills of evidence-based medicine. Evidence-based medicine begins and ends with a single patient. Skill number 1 is how to formulate a question. You'll see a methodology called PICO, Patient, Intervention, Comparison, Outcome. Please don't write this. I beg you. The second skill is once you've transformed the situation into a question, then you seek the best evidence rapidly. So 1 is formulate the question, 2 is search for best evidence rapidly. 3 is critically appraise the evidence. There you are looking for bias. What could deviate the truth of that sample, derived from that sample, away from the truth in the universe? 4th, you will apply that evidence back to your patient. What's the first skill? What's the 4th skill? What's the 3rd skill? Analyze. And we're looking for bias. What's the 2nd? Pardon me? Rapidly search for best evidence. Why did I give them to you in a scattered order? Because I want you to really think about it. It's like tennis. You don't repeat the same movement over and over. They hit you with different movements. Same with playing an instrument. Challenge yourself to think about things like that a little bit differently. Here's your case. This is what you're going to be looking at in case number 1. It's a 26-year-old female with an acute exacerbation of asthma, treated with standard therapy in the emergency room. One of your colleagues asked you, I want to mention this, you've already put the patient on oral steroids. That's an anti-inflammatory drug, and you're going to learn about this in your sessions. Your colleague, who's just kind of nosing around, asked you, well, I just heard that they're using inhaled steroids in addition to oral steroids. So a double whammy of steroids. Why aren't you using it? Well, that sets the tone. What's your first? That's the real patient. Evidence-based medicine begins and ends with a real patient. What's your first skill you're going to apply this afternoon? Formulate a question. We're not going through that now. Second, rapidly search for best evidence. In reality, probably what you would look for is a meta-analysis, which is a form of systematic review. In this study, in this workshop, the small group sessions, we've already chosen one article. It's kind of artificial, but we have to start somewhere, and we wanted to keep it simple. So you're seeing one piece of the evidence. And we, through our search, identified this article on inhaled budesonide plus oral corticosteroids. It's exactly the question we want to answer. All right, what's your third skill? You're going to analyze it looking for bias. What are the three circles of evidence-based medicine? Scientific evidence, clinical experience, patients, values, and rights. Rational, emotional, ethics. Okay? When you analyze the article, you're going to look for forms of bias, and you will learn that as part of each workshop. This form, by the way, will look very similar, this worksheet, whether it's treatment or harm. Diagnosis is a little modified, but the same steps are applied. Skill 4 is what? Apply it. No study was ever done for your patient in your city. We always have to tailor the evidence, like clothing, to a given patient. We have to also translate all these concepts down to the educational level of the person sitting in front of us. What's the key thing about what do we do with the patient? How do we find out these things? We communicate and we involve the patient and family, where necessary, in the decision-making process. What's it called when doctors make all the decisions? Paternalism. Means you're going to do this. Thank you, doctor. That went out decades ago. Now we involve people in the patients in the decision making. I read yesterday 60% of patients with cancer have at least 6 people looking on the internet for information for them. It's a staggering change in healthcare. Think about the internet did not exist in everyday use until what year? 1995. We are 1 decade into this. It is already profoundly changing. And that's why we mentioned information access is a key component. That's also why the Lilly Library, Medical Library, is involved in this course. I love that site. I'm going to put a plug in. I use it. I actually kept track. I use it 5 days a week. It is that good. To look up full text articles, to do searches on Ovid, and then Medline. There are many, many others that you're going to learn about. Let's talk about treatment. Why are we talking about treatment? Because our question is one regarding a treatment. I want you to know that treatments don't just involve drugs. This could be devices like pacemakers, manipulations like physical therapy or acupuncture, or preventative like immunizations. They all fall under treatment. We're asking, in this patient, should I add this new drug? It's new to me. I don't know about this inhaled steroid. I want to learn about it. I want to know, is it good enough? Is the evidence compelling enough that I should start offering it to patients? So, concept about treatment. When we talk about risk, most people think of risk as a negative outcome. In epidemiology, risk is the probability of developing a bad outcome or a good outcome after exposure to something. It could be exposure to an infection, or it could be exposure to a treatment. So don't freak out when you see the word risk used to look at benefits. All right, so go to page 8 of your handout. On your template to critically analyze articles, the first part, I want you to squint real hard. It says, number 1, are the results valid? We're looking for bias. Number 2 is, what are the results? And there we're looking, how large were the results and how precise were the results? When we look for a point estimate, what are we going to also ask to see? Confidence intervals. Very good. 95% confidence intervals. Precise means how large or how narrow are those confidence intervals. Very, very good. All right, let's move on. How do we know how large the treatment results are? What's the first image that should pop to your mind? The flea. What are we going to look for? 2 flea things. Relative, absolute. There is method to this madness. We're going to look for relative and absolute. When we look to relative, we have to have some kind of yardstick. Relative to what? To some yardstick. Okay, let's move on. Page 9, evidence-based medicine loves 2x2 tables. Look at this table. On one side, we can put the treatment groups, either experimental or control. On the other side, we can put outcome of interest. Please, please don't memorize which way something goes. And for God's sake, don't memorize A, B, C, D. Because if you forget what quadrant is which, learn the concepts. All right, concept. All outcomes that we study must be what? Measurable. What is the main outcome of this study? I have thoughtfully put the answer in front of you. Incidence of relapse defined as an unscheduled visit for worsening asthma symptoms in budesonide versus placebo. And remember, everybody's getting all the other treatments the same. We have to declare a main outcome, and that is declared. That's not the only thing we're going to study, but we have to have a main outcome. The reason for that is so we can calculate a sample size. Let's not get involved with that now. Let's move on. Evidence-based medicine Hart's 2x2 table. We're going to construct a 2x2 table with the outcome, which we placed at the top here. Did relapse occur by day 21? Yes, no. And we're going to put the treatment groups over there, inhaled budesonide, control, and we're going to fill in the 2x2 cells. They should add up all the way across, all the way down, and for the total. I do this on every study I analyze. It's even more important when you get to diagnostic tests. Learn how to do this. Create the table, understand what they're doing. I have thoughtfully filled in, because we care, the cells for you. Now, if you read the results, you will see, and it's highlighted, that there was a 48% relapse reduction. Well, the first term we're going to learn is relative risk, the flea. Relative risk equals the experimental rate over the control rate. What's the experimental rate? It is 12 over what? The I want to analyze what percent had a relapse in the inhaled budesonide. How would I calculate that? 12 divided by 94. So the event rate is what? 12.8%. The event rate for the control is what? Do you think this drug worked? Look at the numbers. Did this drug work? Did it prevent relapses? What's the relapse rate in your inhaled, the experimental group? Approximately what? 13%. What is it in the control? Almost 25%. Who had the most relapses? Does the drug work? For this outcome, yes. You can just look at the numbers. Are you statisticians? No. That's just common sense, common clinical sense. All right, there's a problem though. When we put the 12.8% over the control rate of 24.5%, we come out with 52%. Yet it says 48% risk reduction. Turn the page. That is talking about relative risk reduction, which is 1 minus the relative risk. So if you subtract 52% from 1, what do you get? 48%. By the way, when you convert percentages, make sure you convert them to the decimal point. I will tell you, as simple as that sounds, if you make that mistake, you'll be off by an order of probably 2 exponents. You have to convert instantly a 58% to 0.58. Just get in the habit of doing that for any calculation. Okay? Relative risk reduction in human English, inhaled steroids in addition to oral steroids decrease the risk of relapse by 48% relative to control. Well, there's a problem with relative risk and relative risk reduction. Look at the next graph. You can work this out in the privacy of your own home. Both of these, the left side and the right side treatments, have a relative risk reduction of 50%. Which drug do you want to be taking? Which has the biggest bang for the buck? What's your common clinical sense tell you? An 80 to a 40% drop in heart attacks, we would be jumping around in the streets with champagne. Partying. You never see that kind of drop. An 8 to 4% is a relative risk reduction of 50%, but it's not as impressive. What's the difference between the 80 and 40% called? Think of the whale. Absolute risk reduction. Very good. Let's move on. Beware of relative risk reduction because it is not looking at absolute risk. We want, as scientists and clinicians, to look at absolute risk reduction. You now know how to calculate the experimental event rate, and we're going to jump all the way to page 13. What's the absolute risk reduction in our scenario? What is it? Just tell me how to do it. What numbers are we going to subtract? We're going to subtract 24.5 from 12.8 or vice versa. The negative signs don't matter, with a few exceptions. So what's the absolute risk reduction? Pardon me? It's 11.7%. Does everybody see that? That's the absolute reduction of risk of having what? A relapse of asthma after discharge from the ED, emergency department, as measured at what time? 21 days. Perfect. Now I'm going to introduce you to NNT. It does not take a rocket scientist to figure this. In fact, skip all the way to page 15. NNT is 1 divided by the absolute risk reduction, which is what? 1 over what? It's 1 over, and there is a mistake on this slide which we corrected. Here's where you do want to note, in the equation, NNT equals 1 over ARR equals 1 over what? 0.117. That equals 8.5, and for NNT, we round it up to the next whole number. So what's the NNT? 9. Proving to you that there is method to this madness, I'm going to ask you now to look at the next slide, which is screenshot captured directly from the article. Look at the last sentence. Using this approach of giving inhaled steroids plus oral steroids, as few as 9 patients would require budesonide, the inhaled steroid, to prevent 1 relapse. NNT is the number of patients we would have to treat to prevent harm or achieve a benefit for the outcome that we're studying, as measured in this case at 21 days. Think how far we just came in literally 50 minutes. We've introduced why you're here as doctors. We talked about the importance of science, looking for bias, point estimates, and confidence intervals. We discussed the 3 intersecting circles of EBM, which are what? Scientific evidence, clinical experience, patients' values and rights, or doctors' values and rights for that matter. We talked about the 4 skills, and then we talked about risk reduction, relative risk reduction, absolute risk reduction, and number needed to treat. Did you think you would get this far? Raucous applause!